think the joys of this particular type of lecturing is that I can get a fresh coffee in between little segments here. I want a Keurig in all my classrooms eventually, I guess. With the biodegradable pods, right? That's the only way to do it. All right, so we're going to take some stock here. I think I'll take stock in what do we know? In general, we have been looking at how to classify ODE, and in detail, we know first order ODE. Right. We have when y prime is equal to some function of x and y. We can use direction fields to talk about the behavior. Right? We can describe our system. Sometimes with the ability to get answers. We could find terminal values and asymptotic behavior as the fields approach particular values, especially in the case of autonomous equations, where the independent variable did not apply in the slope field, and so we had the phase plane that we looked at. The phase plane making a phase line, which we'll explore in more detail as we wrap things up. And then we said, well, hey, you know what we can do? If this function here is in the form of a variable in x and a variable in y, we can separate them. We can separate the equations. And then we were like, well, even better. Or if it's not separable, maybe it's linear. And if it's linear, we could use either the variation of parameters, var params, or the integrating factor, right? Both giving us the same solutions. This builds into other ideas, and this pops back up all over the place. So they're both fairly useful. Notice the plan that we had, though. We categorized all the weird, it wasn't dt dx plus dt dy equals a constant, right? We didn't have partials. So we were in ordinary differentials, and we haven't gotten to the mx double dot plus bx plus x equals some driving function. We haven't gotten to the doubles, right? It's all, the doubles, the second order. It's all first order ODEs, but there are patterns in them, and we look for the patterns to help us solve things. And to be honest, this is most of the easy stuff. We're going to have a problem that happens when it's nonlinear. And nonlinear goes down a rabbit hole of there are 8 billion different ways to solve them. And so what we want to do is the first thing that we can do is if our first order ODE is not linear or separable. And what we can do is we can do a test to see if is it an exact equation. And like most of the techniques you learn, the idea in general is to switch forms or move into a form that's solvable. In this case, we're hoping to find a set of equations we know the answers to. And so what we start with is kind of a proof of why we know the answers to this, and that proof builds the method. Yeah, but it really is a very special case of equations we're going to look at. And so we're going to study exact equations, and the fact that we're studying is like, oh, they must have pop up all the time. There's a commonality to them for what they are, especially in geometric problems because they have geometric analog. But they're very special subset of the nonlinear, and this technique, useful, does pop up in a lot of engineering areas, is the tip of the iceberg. And so let's define an exact equation. So we're going to talk about a contour map. And so I'm talking about 3 dimensions. And so I'm just going to put a little graph over here. And I'm going to say I have, whoops, get my curve a little more curvy. I think your textbook talks about it as isotherms on a weather map. I tend to think of it as contours because I did a lot of hiking on a contour map, except that these don't need to close back in on themselves. We're in a localized area, and we have these curves that everywhere along one of these curves, everywhere here, is some constant value. So on the weather map, it was all the places that had the same temperature. On a contour, it's everything at the same elevation. And so usually there's a way to move from one constant to another, which you're going to be learning in Calc 3. It's called a gradient. It's how you change in functions. But what comes out of that is everywhere along this line computes the same number. So we could think of z as being the value of the constant, and some function of x and y always gives you the same z value. And so we're going to use this fact that we have things on a contour. We're going to say that we have a function in the form of f of xy is equal to a constant. Now again, we are looking at a very particular type of function. We're going to get some behavior of this function, and then we're going to say, because of this behavior, whenever we see that, we can solve our differential equations a particular way. Right? And so this is the type of function we want to look at. We want to look at some function in both x and y where it always equals a constant. And a good mental image of that is some xy plane where the value of the curve is unique. And a contour map is a contour map, or some isotherms are probably the most used analogy that you have come across in your day-to-day existence. Coffee is good. And so everywhere along the curve has the same value. Well, so we want to think about this being part of our differential equation. In fact, we kind of want to think that it holds the place for our slope. Right? Remember our slope, our first order differential equations we could do in the form of dy dx equals some f of x. We're going to say, hey, we're going to use this to find our slope field and move from there. So what we want to look at is what happens, how do these things change? And so if I take the derivative of this, so I'm going to take the derivative of f of xy. And let's see, I want to make sure, using the chain rule and partials, and I'm just going to state this as a fact, and then we're going to look at physically what it means, all right? Festus will hopefully dig into this a little bit more with you. But I can take the derivative with respect to x, and I'm chaining my two derivatives. So I get df dx with a partial in x plus df partial in y to dy, and I take the differential of the constant and I get 0. Right. So I want to state this as a fact. It's something you'll dig into more, but I want the physical understanding of what it's doing. If my function lies on this contour and I move within my function, tangent to it, right? So I'm not tangent in the xy plane, I'm tangent to this function. So I'm moving always on the same contour. And so this always has to equal 0. I'm not moving up or down tangentially. I'm moving tangentially in the kind of the third dimension here. I'm following this curve, because that's the curve I have to move to, and I'm moving in a way that I'm tangential to it. Well, because this is a constant, I'm always staying at the same z value. And so however much I change in my x direction, and however much I change in my y direction, they've got to add up so that it's not affecting the level curve I'm on. So think about it. I don't know if you've ever gone hiking and you want to stop climbing, you walk level, right? You make level. We kind of design switchbacks to work their way up, right? But if you're ever hiking and you get to a steep part or whatnot, you can walk level. You don't go up or down. You don't go up or down. You don't go up or down collectively, right? Because this is the up or down direction. And so whichever way you move in x and y, the differential it has with respect to the function shouldn't change it. And so that's the physical intuition that we're looking here. Is we have some function, it's kind of hanging out in third dimension, but the third dimension we're always keeping the same. And so whatever change we have of that function in the x, plus whatever change we have in that function in the y, should cancel out. And so that's what we're going to do. And that's what we're the fact that we're going to use to create a set of equations we're going to look for. Alright, so let's rearrange what this is into something that's useful for us. So I'm going to subtract from both sides. So df dx is going to equal negative df partial in y dy. Alright, so I pulled it over to the other side. And let's see, I'm going to put, well, I'm going to divide by dx. So I'm going to get dy dx over here, right? If I divide, but dy dx is so important to me, I want it on the left-hand side. So I'm going to divide this over, and I'm just going to say, hey, what was my right-hand side? It's not my left-hand side, right? I'm just organizing here, bear with me. And then I'm going to divide this over this way. And so I'm going to get a negative, because the negative side is going to come with this. So, so this is going to go over here, and that's going to give me this. And then this is going to divide over here, and I'm going to get my negative sign, and I'm going to get a partial of my function with respect to x divided with a partial of my function with a respect to y. And so notice here, this is a first order ODE. And so what I'm wanting is my first order ODE is going to have this form. Because that's going to tell me what the initial function is. All of this, the function equals a constant, is going to be my solution. So I've used this fact that a particular type of motion in the xy plane creates this partial differential form. Now, I know a lot of you have not had partials yet, so I go to the physical analogy. If I am on some contour and I stay on the same contour, whatever I change in the x direction and whatever I change in the y direction as I move in the plane should not change the z direction, my up or down height. That's what this means. And so if I take that form and rearrange it, it looks like I have a first order ODE that I can look for. And so this is the form we're going to mutate, and we're going to mutate this form to get some work out of it. I'm actually going to record this lecture in little blobs, right? I want you to digest this, be happy with the idea of the contour. I'm going to come back, and what we're going to do is we're going to enforce something from this form, and we're going to move that form into giving us a solution. This was going to be the bulk of today's lecture, so I'm going to do it in little chunks. You know, I've got about 6 pages of notes to make this form work. So sit here, make sure you're comfortable with why we've done this transformation, and then move on to the next slide.